Hello? Hello? Test, test. Ah, jeez. Nothing. I'm just having an audio. I'm just having a hardware failure, that's all. Test, test. Hello? Okay. Hello? Alright, I'm gonna try restarting the computer. See if that helps. Um, so, my apologies. I'll be right back. Alright? I'll be right back. I'm just gonna do a system reboot. Testing, testing. Alright. From future import braces. Ooh. I think that's working. Is the audio okay? Like, how's the volume level? Yeah. I don't know what it was. It was my my little webcam, which is not the built-in webcam, went went dead for a bit there. I was having flashbacks to when my condenser mic lost its ability to pick up sound, and only on my computer, which is a thing. Oh, I just pulled it off. Oh my god. Alright. Alright. Try not to get it in my tea. Alright. I think I'm just about ready to not have to do streaming anymore. I think I'm ready to get back to in-person classes. How about you guys? Good. Anyway. Ugh. How is everybody? Sorry about the technical difficulties. That's what I get for not checking before I go live, eh? I have to commute, so I'm not that eager. Yeah. 8:30 class, ooh. Commuting plus 8:30 class, that's the worst. Yeah, much nicer socially. Like, I have, like, it's been my conscious effort to try to, like, encourage the social, you know, through the chat, because, like, I know that this is in no way comparable to actually being in a classroom with your actual colleagues, you know? Like, this is like approximate at best, but I feel like, you know, the least we can do is, like, kind of be chummy over the chat. I think that's at least, you know, that's something at least, you know? Socialization is nice, but it's a distraction from homework. Yep, that's true. Hockey intramurals. Hockey, I assume you mean hockey. During your 2 8:30s. Oof. Woof. Yeah. Yeah. Yeah, I hear that a place to sleep in or around campus is getting really difficult to find and expensive, so I hope everybody who wanted one has already got one. So, anyway. So we had just finished off this big, the big example, with respect to, assembly programming. Very simple program relative to C standards. All it does is take an array of 5 values, and then sums the array, places that result back in memory. This is something that you could do very quickly and easily with a C program, and something that you can do, like, call one function in Python for, of course. But in assembly, you see that the procedure is quite a bit longer. But yeah, so we had just done that. We just taken a look at the memory. We just had the one slide left, actually, in this lecture, and then we were going to get on to other stuff. Let me just put this over here. Bop. Box over a sewer grate. I mean, that's boxes over sewer grates would actually be, like, much better than that would be like premium box real estate, because it's got a built-in bathroom. You know, most of the boxes that you see on the market these days they aren't even over sewer grates, so they don't even have a built-in bathroom. It's like communal bathroom in the one corner. It's just a pail, like a steel bucket, like 1930s style. Yeah. Probably about the same level of infestation with vermin as most other student housing. Ho ho! Don't about the heat from the fresh poop. Yes. Yes, it's got the... Touché. Anyway, so let's just wrap this guy up, and then we'll get on to bigger and brighter things, shall we? So, a note on indexes. Do you notice how we are incrementing R3 by 4 each iteration? R3, just to recap, is the register in which we were holding I. Built-in HVAC, yeah. You even get the city to sweep your house for you, like once every 3 months or so when the street sweeper goes by. Yeah. So R3 is the it's the index, right? In a normal loop, this would be I, right? The thing that you count up to get through all of the different elements in the array, right? So the interesting thing about this is that we're increasing it by 4 each time, which is actually the word size of the things stored in memory. So one of the things that C is very nice and handy and does for you, as it turns out, is it actually, when you request an element of an array, it actually offsets the memory address by the word size for you, so you don't have to worry about the word size of the array as you're trying to process it. Not so in assembly. Yes. Yes. You may also have noticed that assembly doesn't have a type system. This is like really programming without a safety net. This means that you will have to manually align your pointers to words in memory. Since integers are 4 bytes in size, we increment by +4 rather than by +1. The memory map can verify for you what the word sizes are for a specified operation. School itself is great, but the housing? No. Every day I wake up in Hamilton. Oh, are you a Hamiltonian, Ethan? I'm a Hamiltonian. I've lived here for a while. And I didn't, move here because of school, either. I would consider myself to be a native Hamiltonian at this point. I think I've gone native. But yeah, anyway, so that's just the last thing wrapped up. Assembly. Are there any lingering questions about assembly programming? Are you all confident that you could produce an assembly program, if required, on, for example, the final exam for your favorite course this semester? Possibly. Possibly not. I am indeed a Hamiltonian. Since I have lived here for 4 months, I am therefore one with Hamilton. Give me a code sheet. And I can do so. Yeah. Well, if you go to the Visual website, they've got a table of all of your operands and all of your operations. Command sheet, equation sheet equivalent. Yeah, I would say command sheet. If it's assembly, then you are programming in commands. How do you do characters and strings? Next question. I don't know. I don't know if it's possible with Visual. So, I wanted to pull in some additional hexadecimal, probably. Well, it's interesting, right? Because with strings, you don't do a whole lot of direct manipulation of the string values themselves, and we know that C likes to treat strings as if they are 8-byte characters. So, yeah, just pretend they are integers, and then ASCII would be easiest. Yeah, really. Just pretend they're integers. I know that, like, a printf in assembly is, like, a complicated process. Printf assembly hello world. Let's see what comes up here. Not WebAssembly. Let's just do x86 assembly. That doesn't look like assembly at all. This is very complicated. Oh, here it is. So this is what I could find. Program hello world. This looks like it's been written in x86 assembly. So you've got some operations here, which I don't understand. You've got some operations here with it, which I don't understand. You've got the message itself, which is, there's a string, ho ho. Yep. This looks pretty complicated to me. Solution number 2. Good God. Yeah, okay. Does assembly take user inputs, or should we just not worry about that? You should just not worry about that. Yeah, please, there's a reason that I cut off assembly programming at the level that I did. What is the average difficulty of assembly code we will be expected to code for this course? Well, I can show you what the assignment 5 questions look like. That'll probably give you an impression. I don't know. Has assignment 5 been posted yet? Should be. If it isn't, it looks like it's ready. I'll get it posted by the end of the day if it's not up there already. So you got 2 questions. This one is an if-then-else. So there you go. Very simple. Very cool. The second one is a little longer. It's the Collatz conjecture. Yep. This one's a little trickier, but still good. You have to do a little bit of bitwise to determine whether or not it's even or odd, but other than that, it's I think this is achievable. But this is, I would ask you a question no longer than this one for sure on the exam. Is it up? Okay, Kevin thinks it's up. We will go with Kevin's version of reality. So, okay, so I wanted to sort of shift gears a little bit now and talk about some of the sort of peripheral programs that you can use in order to analyze and test your C programs. But at first I'm going to answer David's question about the assignment. For question 1, I understand the part of conditions, but what values are we supposed to set R0 at the beginning? Or will you while marking input for R0. So for that question, it's like you can just set them with values at the beginning. You can set, like, that's how you would call, this is how we're going to consider calling the function, right? You write some values into the register, then you have the block of code that does the if-then-else, and, you know, so you get to modify those. There's no specified, like, inputs. But yeah. When is it due? I believe it says it's due Sunday, December 5th. So the Sunday of the end of week, the end of classes. We'll see. I'm open to the idea of doing an extension for that. Watched a video of someone testing the same algorithm in C#, C++, assembly, and Python. Ran through the algorithm 5 times in 5 seconds. Assembly 7,436 times in 5 seconds. Holy crap. Alright, thank you. That's very cool information. So, by that calculation, programming the same program in assembly versus Python gets you over 1,000 times as fast. That's crazy. That's actually crazy. Sifting out 1 million primes. Yeah, okay. That makes sense. That's basically Bitcoin mining. The end is nigh. You have to say the end is nigh, not the end is near. Anyway, so let's talk about makefiles. Makefiles really are something we should have talked about a long time ago, but, you know, here it is. So, we're going to talk about makefiles and introduction, using variables in makefiles, automated testing using diff, static analysis, and then we've got some an appendix at the end. So, let us recall the stages of compilation. Your source code gets thrown into the preprocessor. The expanded code gets thrown into the compiler. The assembly code gets thrown into the assembler. The assembler produces object code, which gets sent into a linker, which pulls in library files and object code from other sources, pops it all together, produces executable code, and then you execute it. So, the preprocessor directives are first resolved, then parsing and AST generation, assembly of object or machine code, and then linking with other files if applicable. Yeah. Primes from numbers less than 1 million. Yeah, that. Actually, you know what? Even though you didn't say that, that's actually what I assumed you meant by that. Funnily enough. So what is the point of object files? An object file is machine code that was compiled from its source code, but without the code for any called functions in other source code files. Instead, object files contain links to the needed functions in the needed files and libraries. Object files are binary encoded, not character encoded, so there's no point in trying to look at them with cat or less. By compiling an object file for each source code file separately, the object files only need to be updated if the source code is updated itself. This can produce a massive speed boost in compilation time. So, this is the scenario, right? Let's imagine that you have a long, complicated C project, right? Something like the Linux kernel or something like that, right? Your file, if you're a good programmer, will be modularly broken into a bunch of smaller files, right? When you're working on the project, generally speaking, if you have compiled one of these libraries already, right? And you don't make any modifications to it, there's no reason that you should need to recompile it. As some of the more experienced coders in the crowd will tell you, compilation time can be non-trivial. Like, compilation time is mostly trivial at the level we're doing things right now, but once you start getting into sufficiently complicated projects, it can take, it can take 10 minutes to compile your project. It can take half an hour to compile your project completely, which is a lot of time, right? So this was kind of a solution to this problem that was developed back in the days when computers had much less horsepower, and these types of optimizations meant the difference between, getting, being able to do, 15 compilation runs in your regular average workday, or something like 100, right? Yeah. My SE friends were doing a lab that took 10 minutes to compile and 20 minutes to run. Yep. Tell that to the 15 nested loops I use whenever I have the chance. Yes. So essentially, you have object files, right? You don't have to recompile every source code file every time you compile a project, right? This kind of, this mindset is built into the ethos of pretty much any IDE that you use that would be sufficiently complicated. Visual Studio, for example, will do this by default. It'll only recompile the things that have changed, right? And so the fact that we have object files allows us to only recompile stuff that's changed, right? Because linking, this is the reason that linking isn't done all at once, right? Linking is done afterwards because the object files, when they're separately saved, they haven't necessarily changed, right? So, using object files correctly requires effort. We can compile a batch of source code files to object files using glob patterns and the C flag. If you haven't heard of the term glob pattern before, this is a glob pattern. Star being the multi-character wildcard character, that is a glob pattern. Don't ask me why they call it glob, but there's probably some reason. So, in GCC, you can compile to an object file directly and not produce an executable using the C flag. But then when we go to compile our program from the object code, for example, GCC output file main, input files main.c, lib1.o, lib2.o, lib3.o, etc.o, we have to manually include our object files, which is tedious and time-consuming. So we're saving compilation time, but we're losing time to longer commands. And of course, as everybody knows, the slowest part of any computer system is the operator. There has to be a better way! So, make is a program which automates the compilation process. Make compiles only those source code files that need to be recompiled to produce an executable when properly configured. It does this by checking the time at which your source code files were last saved and the time when the program was last compiled. Make requires a special configuration file called a makefile, which tells the files, tells it which files to compile, which compiler to use, and all kinds of other stuff. Makefiles are not bash scripts. Bash scripts are different. You can call bash scripts from makefiles, but makefiles are something else. So, the way that it determines this, the way that it determines whether or not a file needs to be recompiled is purely a calculation. It's purely a subtraction over timestamps, right? So you tell the make file where the object file is, right? When the make file is invoked, it examines the date last modified, or the timestamp, on the object file, compares that to the timestamps of all of the files that are required to compile the object file. If any one of the timestamps of the input files is greater than the timestamp on the output file, it'll recompile it. Otherwise, it won't, right? Because if the timestamp of all of the input files is less than the timestamp of the output file, then none of them have been updated since the output file was produced, so you don't have to update the output file. Make sense? Hopefully. So, makefiles are composed of rules. Rules have the general form target, prerequisites, and recipe. A target can be one of the three following things. It can be an executable file, an object file, or a so-called phony target, which functions as a special command. Prerequisites are the files that are used as input to create the target, and a recipe is a bash command that performs make performs to create the target. Each recipe line must be started with a tab character. Spaces are invalid syntax. So let me see if I've got a. Let's see if we can put together an example of this. Do I have a good example in? Sometimes I put good examples in, like the here. Yeah. All right. Okay. Apparently there was a meme hiding out in there for some reason. So. So I realize for you Visual Studio guys, which is probably most of you, this is probably not going to make a lot of sense because you haven't been compiling things by hand all semester. But for those of you who have, this should make some degree of sense. So let's take a look at the structure of this code that we have, right? So we've got top.c, right? So top.c includes mylib.h, right? Mylib.h, if we cat that, contains some function definitions and a definition for a function. It contains several function definitions, shall we say. I've also got sea shanties, which is a fun little program. Also a pun. That has the definition of Barrett's Privateers, the function, in there. So, essentially, we need all three of those files in order for the thing to compile. And I think we need one more as well. The, let's see here, cat, sums and products.c. Yeah. So, why did I include mylib.h with quotes and not with angle braces? Because it depends. So if you remember way back to the beginning of the course, we talked about the difference between these two. Angle braces means it goes out and looks for it in the standard library folders, right? Quotes means that it's a local library. So mylib.h, it's a local file. It's not off in like the standard system library directories, so I need to use quotes. So let's write a makefile. Let's move the existing makefile to makefile dot old, and let's get it a new makefile. So our top level thing that we're trying to produce is an executable called top. So we specify the name, right? We put a colon. For some reason, when I looked it up, they said angles were used in C and quotes were used in C++, but that's obviously wrong. Yeah, I mean, I don't know C++ well enough to know how true that is, but minimally C++ should also, like, so the thing about quotes will also search the system directories, but it'll search local directories as well. So you could, technically speaking, use quotes for everything, right? But angle braces specifically means it's off in the system libraries, and you have to go get it. So you could technically use quotes for everything, but it's still useful to distinguish, I think. But, you know, your mileage may vary. So, to compile top, we say our output file is top. We require top.c, and we also require, we don't need to manually import mylib.h because that is provided for in the source code itself, but we will need products.o, sums.o, and cshanties.o. So these files, which are necessary for the compilation of top, are the prerequisite files. So the way that the makefile works, this is the output file. These are the input files. This first line is what the timestamp calculation is based on, right? Then it executes everything past that point. So this is good. So let's see. The thing about make and makefiles is in order to perform the actions in a makefile, you just type make from the command line. Make. There you go. So you see, it didn't have output files for these guys, right? So what it did is it just kind of substituted in the default compiler in Unix, which is CC, with not GCC, although I think CC points to GCC, but we can make it explicit. We should make it explicit. Why are they .o and not .c? Because these are compiled object files, right? So let's add in some rules for the rest of them. Products.o requires products.c, GCC with the C flag. Output file is products.o. Input file is products.c. And then just, you know, a little bit of copy pasta. There we go. And so, you'll notice, if I try to re-invoke make, all of the .o files that have been produced are, like, everything's up to date, so nothing is recompiled, right? If, on the other hand, I touch is the Unix command for updating the timestamp while changing nothing else. So if I touch sums.c, you can see LSLA, you can see that sums.c has a slightly more recent timestamp than product.o. So I made product.o 2 minutes ago and sums.o 2 minutes ago. So if I invoke make, you'll see that the only things it recompiles are sums.o and the top level file. There you go. Ta-da! And if we invoke top, everything has been compiled correctly. So, any questions about stuff so far? This is like basic level makefiles. There are more advanced things that you can do with makefiles that we're going to talk about. But, yeah, any questions? Okay, I don't understand what you did with touch and what was shown when you typed make. Okay, I can go over that again. So, touch, touch is a Unix command that changes the timestamp of files. When you have no time, like no flags specified, all it does is it updates the timestamp on the file that you touch to the current time. It's actually, touch is a command that you can use to alter the timestamps on files that were made in the past as well, which is why when people, come to me saying, oh, I finished my assignment on time. Look, see the timestamp? I'm like, you can modify the timestamp. All you have to do is Google, how do I modify the timestamp? That's not evidence that you submitted the thing on time. I don't get the significance. Okay, so I will, so here's the significance, right? So if I view the timestamps for all the files in this directory, right, notice that some, like products.o was modified, that was last modified at 10:08, right? If I touch, products.c was last modified in August. So if I update products.c, this basically simulates me making modifications to the file, right? Touch is just like, I could go into it, open it up with a text editor, like change something in the file and then update it, and that would also update the timestamp. This is just a faster way of doing it. So if I touch products.c, you'll see that products.c's timestamp has been updated. So when I invoke make, it knows because products.o has a timestamp that is earlier than the most recent update to products.c, it knows that it needs to recompile it. So it performs this recompilation, right? So it doesn't recompile sums or sea shanties. It doesn't recompile these two. It only recompiles this one, right? Then, because this guy gets updated, right? That would mean that one of the timestamps on one of these files is now more recent than the timestamp on top, which means that top also gets recompiled. So essentially, it's like top has products as a dependency, the dependency gets updated, and make automatically updates anything that has it as a dependency. Just wondering why in the first GCC we don't need the C flag, because we're not compiling top.o, we're compiling an executable file, right? Like the .o files are not executable. If I take a look at cat sums.o, for example, you can see that this is like largely like binary data, though there are a few bits in here that are not. Right, like the version of Ubuntu, or the version of GCC that this was compiled under is not. That is stored as a string, but everything else isn't. So does make, when typed in the terminal, just tell you what it had to recompile, and then the second line is everything that is then used in it? So what it's doing, let me just, there we go. So let me just reproduce that. So the make function, or the make program, looks up the make file, looks up the file called makefile, right, and then executes it. It prints out to the terminal all of the commands that it executes. So, for example, if I were to throw another command on one of these, like echo now compiling product.c, touch products.c, and then make, you'll notice that it tells you what command it executes. It then executes it, then it goes on to the next command. Right? So, basically, this is how you get around if you're not working in an IDE that has a compile button. The compile button in Visual Studio Code is doing this in the back end. This is what the run button does. Right? So, this is good. Good. So, I think yeah. So if something is up to date, it just skips it whenever you use make. Yes, yeah, exactly. Precisely correct, my friend, precisely correct. Like if I were to call make again, having updated nothing, it says top is up to date, so what are you going to do? Incidentally, you can specify, well, you know what? I'm gonna let the slides get us there. So, recall the files that we used. Well, we didn't use. This has been borrowed from 1xc3. Sorry. So, in Lab 6, they used these files to create static and dynamic libraries. We used a lot of fancy compilation methods to create static and dynamic libraries, but you can also use these more simple invocations of GCC. So, you know, you can just do regular compilations this way. But you can also use makefiles to automatically compile libraries, right? In the proper sense. So, if we write rules to produce all the object files and the final executable into the makefile, we get the following, which is precisely what we got previously. The only difference is WALL is being included here. Now that we have our makefiles in place, we can start compiling. To compile the, quote, default goal, simply type make. The default goal is the first one. So whatever the first rule is, that's your default. What is WALL? That is enable all warnings. That's a compiler flag that enables all warnings. To compile any of the targets in the file, you just specify the target. So if you want to make specifically sums.o, you just specify that, or top. To invoke a phony target, again, just type the name. Nothing could be more simple. So we'll talk about the adding cleanup routines to make files next time in class, because we're now out of time. Thank you very much for your time and attention. Are there any further questions? Like, I think one of the warnings that you'll get with WALL if you invoke WALL, one of the warnings that you get is unused variables. So if you declare a variable, but then never use it in the code, it'll give you a warning. I'm pretty sure. Probably I just don't know them yet. Yeah, that's the problem with questions, eh? Once you've formulated the question, you're already halfway to the answer. That's my experience. Can you only have one makefile? I believe so, yes. I believe it's one per directory is what you're permitted. Now, I would say you probably don't need more than one because, like, the only conceivable reason I could think of for you to need more than one makefile in a directory is if you have the source code for more than one project in one directory, in which case I would say something like directories, like the computer isn't charging you to make new directories, so you should probably just make a new directory for the separate project and put the two projects in two different directories, and then you can have separated makefiles for them. And, it's also, like, completely possible to have, like, two different compilation trees in the same makefile, you know? Like, if you, in theory, like, if you wanted, like, to compile something in debug mode and that required some extra libraries, you could throw in some additional rules that, like, do specifically, like, a debug compilation that maybe pulls in the different libraries, and you could have that in the same makefile for sure. The question then would be, what is the default target, right? But, yeah, like, and makefiles can be very useful. Like, makefiles are useful for more than just C files. I've actually, for my thesis work, like, my thesis is a huge LaTeX thing that is spread across many, like, a lot of different directories. And there's kind of like a process for compiling LaTeX when you're compiling it with a bibliography. Like, you invoke LaTeX once, then you invoke BibTeX, which generates the bibliography, then you have to invoke LaTeX 2 more times. So, so I've got, like, a one subroutine that's, like, the full build. I've got a quick build as well, which just, like, it doesn't generate the glossaries, but, like, this takes literally more than three times as long than this one, and, like, it takes a while to process the thesis, you know? Like, if I were to compile it, it takes a while. Because, you know, with the code appendices, it's like 1,000 pages, so. But yeah. And the cleanup routine basically just cleans up all of the different file types that are intermediate file types that are generated during compilation and are kind of just left there. And they just take up space and are ugly, so you might as well just take them out. So yeah, that's how it recompiles. So yeah, makefiles. Incidentally, makefile can be capitalized or not. It doesn't matter. Any questions? No? Have I lost most of the class at this point? Half the class. I've only lost half the class. Wow, we only got, like, peak 22 students today? 23. Ah. Okay, well, take her easy, folks. Office hours today if anybody wants to drop by. Otherwise, I will be seeing you next week. Our last full week of class next week. Bye.